Sorry for the delay, guys. If you have to leave earlier, or I don't know how long this lecture will take, this one is actually a little bit shorter, so maybe we can still finish in time. No idea what was going on here. Anyway, let's try to continue. If the audio happens to break at some point, please let me know. So today's lecture, we are having a short overview of what we're going to talk about. First, I just want to quickly discuss the feedback results, and I have a little bit of a surprise for you. I hope this is going to work, but so far my luck doesn't seem to be on my side today. Afterwards, we're going to discuss the main two topics of today's lecture, which are domain decomposition and load imbalance. So how do we actually decompose domains? How do we split workload? Are there different ways to do it, and are there any ups or downs to doing this? We already hinted on this in yesterday's Proseminar. And the second topic will be load imbalance, which is basically always the case when some processing entities, like ranks in our case with MPI or threads in OpenMP, finish sooner or later than others. This is always undesired behavior. So how do we quantify this? How do we qualify it, and what can we do about it? And the last section is again a Tales from the Proseminar, which is, or which are actually two slides that are already presented, which is just the efficient neighbor exchange of ghost cells. But anyway, let's first go to the feedback results. So I got 11 messages total so far, which is nice. Overall, you seem quite happy with both the lecture and the Proseminar. I hope I can continue to hold this bar high. There were a few small complaints or requests or remarks. This time I only got 2 times the remark that I'm talking too fast, which is 18% considering the 11 messages I received total, and that's a new low record for me, because usually like 50% of the people tell me I'm talking too fast. I apologize for that. I've been working on it for 10 years. Not gonna change, I think. Anyway, maybe YouTube helps because you can simply slow down videos. I don't know if any of you are actually watching my lecture videos after the fact at 0.75 speed or something, who knows. 4 times I got a request for less work, especially referring to the last assignment. I hope I already adhered to that with the current assignment, which should be much less work. Once I got the request for hard resource limits on LCC2, which I already conveyed to CIT, and they said they will investigate. Can't promise anything, but let's see, maybe they can do something about it. Once I got a request also for face video in order to make the lecture a little bit more entertaining. And I don't know if this will actually help. I don't know if you find the lecture boring as it is, or whether you are extremely fascinated by the topic, but in any case, here I am. So I got a stream cam, and I don't have a green screen, so this is using some fancy machine learning stuff, AI, to sort of cut my face and body out of my room so you don't see that I never clean up my apartment. I hope this works sort of reliably, and maybe I will upgrade to something that's not a poor man's green screen but actually a real green screen later on. Let's see how this goes. And I would appreciate also some feedback to let me know whether you think this helps or whether it's distracting or you find me ugly, and just let me know. Okay, now back to actual lecture topics. As always, I want to start with the motivation. Why do we need load balancing? Why do we need domain decomposition? Why do we talk about this stuff? So we had our 2 main problems that you worked on in the Proseminar, Monte Carlo pi computation and the 2D heat stencil. So for those, it's really comparatively easy to compute how much work every rank has to do, or every thread, depending on whether you're talking about OpenMP or MPI. For the Monte Carlo pi computation, the amount of work really depends only on the number of samples. So below I have a very simplistic code example. You have the overall number of samples, you divide it by the number of ranks, and that's the amount of work everybody has to do. For the 2D heat stencil, the amount of work also only depends on the number of elements or cells, and in this case it's just the overall problem size divided by the number of ranks. It's really the same problem, the same issue. Now, what does this look like graphically speaking, and why is this the case that everybody has to do the same amount of work? Because every sample is the same amount of work. So on the left, you see the figure that represents what's going on when you run the Monte Carlo Pi computation. You have a bunch of random points. If you set up your random number generator correctly, then every thread or every rank will get different points. If you set it up improperly, then everybody will sample the same points. The different color denotes what rank is computing which point. Again, it's just a very small visualization. You will get a really bad result with these few points. And every point roughly takes the same amount of work. There might be some differences in terms of what's the floating point number, is it normalized or denormalized, so there might be some minor issues in terms of how many clock cycles you take for each computation. But in the grand picture, in the ballpark of seconds of runtime, there's not going to be any difference really. The same applies also for the heat stencil. So on the right you see the heat stencil or heat stencil example in 2D. Where we have a quadratic problem domain, and we divide it into 4 parts because we have 4 ranks, again color-coded depending on what rank is computing which part, and each of these cells roughly takes the same amount of work. We do have some cells that are different. For example, we evaluate whether we are at the border and we need to implement some specific border condition by checking if I is 0 or if I is n-1. And for these cases, the workload differs a little bit, but again, this is really in terms of a few clock cycles, and we're not talking about an overhead that can be quantified at least in a low percentage number, say 1, 2, 3% or something. It's definitely below that. So overall, there's no load imbalance. Every cell takes the same amount of time. This is what we call balanced load or load balance, which means all of them have the same amount of work. All ranks or all processing entities, doesn't have to be ranks in MPI. This really applies for any kind of parallel programming. And for the programs that we had so far, this is easily achieved, right? The only thing we really care about is dividing the domain into subdomains that are of equal size, because equal size entails the same amount of work, and it doesn't matter where in my domain I am, it's always the same if the size is the same. The problem with that is this really only holds for a small subset of realistic applications. In reality, in real life, this usually doesn't happen, which is the bad thing, but real world and physics just are more complicated than that. For that reason, there's also unbalanced load or load imbalance, what people call like when ranks do not have the same amount of work. That could be, for example, because the size of the subdomains per rank varies, or the entailed amount of work varies, although the subdomains have the same size. And yeah, as I already hinted on, this happens all the time, unfortunately. So an example I want to give that motivates that is Lagrangian type simulations. So far we had our 2D heat stencil as a sort of physics simulation, and in the heat stencil simulation, in the heat stencil computation, you only had fixed grid points, and you compute physical properties at every grid point. But the grid doesn't change. The grid always stays the way it is. So you know that the point at coordinate 2, 2, for example, is always at coordinate 2 and 2. It's not going to move. Lagrangian simulations, on the other hand, do it the other way around. They don't have a fixed grid, but rather they simulate moving particles throughout your domain. This could be, for example, water molecules in a river. And for this kind of simulation, you can't use a fixed grid. You actually need to have properties set to particles or clinging onto particles, and these particles have a position that can change. And because the position changes, and because I told you people like to map the physical domain to hardware topology, because that's usually speeding up your computation. That speeds up your computation because you have adjacent elements also adjacent in your hardware topology, so you minimize latency for neighbor communication and so on. And for this reason, also this information on the particles, the data that represents particles, is moving through your network. And this is why these Lagrangian type simulations are a little bit more complicated than just the fixed grid of your heat stencil. Take, for example, here the visualization where we have 4 different cubes, which are all of the same size in our entire problem domain. And again, color-coded with what rank is computing which cube. And you see that there's no particle in the red cube, for example, which will be no load whatsoever, except for some management overhead probably. There are a few in the green cube, and the maximum, for example, would be the blue cube with a lot of particles in there. So that means the blue rank will have to do a lot of work, and the red rank will have to do no work at all. And this is load imbalance, although the regions are of same size, and this is bad, and we have to deal with that. In terms of CPU and wall time, it's really easy to see something like that, because you will end up with ranks or processing entities in general that no longer have the same wall time for every rank, but differing wall times. And as I showed you in this example, you can have the same CPU time for both cases. So in both cases, if you sum up the times and you compute the CPU time of your entire program, you will end up with 4. Whatever 4 is, we don't need a unit here. And for the second case, however, that has load imbalance, the wall time will be 1.2 because it's the time of the longest rank that executes. So the last rank that finishes its work, if you remember the formula from the measurement lecture. And this is a problem, right? This is visible already in very simplistic measurements just with CPU and wall time. We will have a lecture on performance and profiling a little bit later, but you don't need any profiling tools to see that. This is already sort of evident once you arrive at the wall and the CPU time that differ like that. It's not really a factor of 4 anymore, although you know that you have 4 ranks. This could also be just some static parallelization overhead, but depending on the problem and depending on your hardware setup, you can sort of find a way of just getting these 2 numbers and then figure out this is probably caused by load imbalance and not something else. And this is something we want to avoid. And just a little bit more, because so far we only talked about load balancing, but not really that much about domain decomposition. And those are sort of 2 different things, but I will detail on those throughout the rest of the lecture, so don't worry. For the domain decomposition of the Monte Carlo pi method, we simply distribute samples between the ranks, right? There's no communication, you already saw that. During the computation, we just need a little bit of reduction or aggregation at the very end. And this is why this kind of problem is also called embarrassingly parallel, because it's really easy to parallelize. There's no communication during the workload, just at the very end. The amount of communication doesn't really depend on the number of samples, which is always nice to hear because of O notation and runtime complexities. And the second example that we dealt with was the heat stencil, which just distributes grid cells, and there is a ghost cell exchange required, as we all know, because you had to implement it for the Proseminar. And the reason why I'm presenting these 2 slides here is because those are actually 2 classes of programs among a larger group of classes. So these are called dwarfs. They are, depending on who you ask and how many types of programs you want to include, people like to say there are either 7 dwarfs or that there are 14 dwarfs. And these are just different categories of parallel programs that we will hear about maybe already in the next lecture next week. Let's see when I'm going to do that. But just to give you a hint that these are 2 major examples of 7 or 14 examples total that represent most of the parallel programs out there. So we're trying to cover what can be done, because those are really, you can't map any problem to a Monte Carlo simulation, and you can't map any problem to a heat stencil simulation. That doesn't really work, but 2 of those you already saw. Anyway, let's continue with going into more details on domain decomposition. So domain decomposition basically consists of 3 steps. First of all, we need to discretize the problem space, right? So you could discretize your problem space into grid cells, for example, into individual particles, or into samples in case of our pi computation. But you need some sort of discretization because, well, computers are not continuous, right? They don't work. Even if you have a contiguous array, you still have element number 0, element number 1, element number 2. There's nothing in between. Once you know how to discretize your problem space, you need to split the workload among the given number of ranks or threads or whatever you have. This is beneficial not only for parallelism, I think I mentioned it once already. Don't underestimate also the benefit in terms of reducing the memory footprint. This is one of the main reasons why we can have superlinear speedup. If you split up the program the problem into chunks that are small enough, they might fit in a lower level of your memory hierarchy, and that gives you additional speedup. So consider also the reduced memory footprint. And the overall goal is to minimize overhead, which is then your sort of final step. And that means basically, again, three things. First of all, we want to minimize the load imbalance. So we want to have sort of a domain decomposition that makes sure that everybody is doing the same amount of work, which doesn't necessarily mean same amount of samples, same amount of cells, and so on. You know that. This is what we're going to discuss in the second part of the lecture. The other two parts, which I'm going to discuss first, are minimizing the amount of data that you want to be transferred, because we don't want to overuse network bandwidth or memory bandwidth, for example. But it's not only about the amount of data that is to be transferred, it's also about the number of messages that you have to exchange. Because as we will see later, in the 3D heat stencil example, you can decompose your domain, your three-dimensional domain, in several different ways, and this has a direct impact on the number of messages you need to send and receive. And every additional message incurs latency, and this might be an issue. So that's why we're going to talk about it. The bad news about this is that MPI, which is what we've been using so far, doesn't really offer any domain decomposition. I mean, sure, there are methods like MPI scatter, for example, that allow you to distribute data, but it's really only the underlying tool. There's no automatic means of saying, okay, this is my problem domain, cut it up into slices and send it to everybody else. No, the cutting up and sending and so on, you have to do manually, especially if you have something more complicated than just a contiguous array. Consider individual particles, for example, that might be held in a linked list or something. Then you can't just use MPI scatter and work with different offsets, for example, in order to send information to different ranks. So data structures are usually more complicated than that. You need to really take care of this yourself, or better yet, if you can find one, use a library. So we will also have a lecture on programming models that are different from the basic message exchange type programs that we've been working on so far as an MPI, and also different to OpenMP. Those are called domain-specific libraries or domain-specific languages. And I will show you that there are tools that try to sort of do this automatically, that allow you to just say, this is my data structure, just do everything automatically, decompose and distribute it automatically. I don't want to be involved, just do it in the best way possible. There are tools out there that can do this. Most of them are still in a sort of academic state, and none of them have a technological readiness level that matches MPI, for example, or OpenMP, unfortunately. I hope we will get there in a few years, but we're not there yet, in my opinion. Now, I mentioned that sending individual messages incurs latency overhead, and we should worry about the number of messages. Why is this the case? Well, very basic. It's the cost of a point-to-point message that really annoys us, right? So on the top left, you see the formula for computing how much time you require for a single message, and it's quite easy in its simplified form. There's the latency that you have in the network anyway. So it's just the time you need to get information from A to B. If the information is has no payload, for example, so if it's just like a single bit that you're trying to send, just a single piece of information, and you add to that the message size divided by the bandwidth, which shows you the initial or the additional time overhead required to transfer a certain envelope of payload, right? So this is quite easy. The thing is, it's a very simplistic view, because the actual cost might also depend on the underlying protocol. I already hinted on that that MPI offers or uses different protocols for exchanging messages, like the eager or the rendezvous protocol, which I'm not going to go into too much detail in this lecture. If you're interested, just let me know and I can elaborate on that. But basically, this is one of the reasons why MPI might block for messages of a certain size and might not block for messages of another size. Because if the message is small enough, you can just send it to the receiver, because you can assume the receiver has a buffer of this size anyway. And if the message gets larger than that, you might need to do a handshake and negotiate on buffer sizes first, if you try to send 1 gigabyte at a time, for example. So this has an effect, and this is obviously not covered by the formula we have here. Because it increases the latency, it increases a little bit the message size overall, because you need to send additional messages with meta information and so on. Also, this formula ignores additional data copies that might be required. So if you use a buffered send, for example, you will have allocated a buffer beforehand, and copied data there first by MPI, or have MPI copy data there first before sending the data, which is an additional mem copy operation. If it's copied into a buffer of a network card, it could be traffic over the PCI Express bus, and so on and so on. So these are all really not covered here in this formula. Now, how can we work with that? So how does this help us really? The latency and the bandwidth are really fixed properties of the hardware topology, right? The latency sort of is a property of the speed of light. And trust me, the speed of light is really a limiting factor here. So that's one of the reasons why we can't make networks any faster. That's one of the reasons why we have stacked memory, where people try to put memory modules onto CPU cores in order to just minimize the distance they have to travel on the main board, or actually remove the distance over the main board and just put them on the same package. That's one of the main reasons, because there's the speed of light, we can't get beyond that, there's no information travel beyond the speed of light, and this affects our latency. And the bandwidth of the network is also a fixed property, right? It depends on what network interconnection you have, the memory links that you have, the links that you have between CPUs, for example, in order to communicate between cores. You can't really influence that. You can only select smarter rank core mappings, for example. If you know you have link aggregation, you can try to use multiple memory links at the same time in order to increase your bandwidth, but that's really everything you can do. You can't just request more bandwidth from the network. What we can influence, however, is the message size and how many messages we need to send and receive. And this is really where we try to be smarter. And for regular decompositions, for decomposition of simple regular rectangular grids, for example, this actually can be computed quite easily. So I already mentioned that I'm going to talk about this yesterday in the Proseminar, so today I'm going to show it to you. I'm going to present you with 3 different ways of decomposing a 3D heat stencil grid, which gets sort of increasingly more complicated, and I'm going to show you then the trade-off between these 3 variants. So what we have here on the right is always the cube of your 3D domain, and with the individual colors I try to illustrate how you decompose your domain, right? In this case, we decompose it into something that people like to call slabs. So we just take slices by only decomposing in single dimension. And if you do that in a single dimension, you end up with a communication volume, which is this formula here, which is the amount of data you have to exchange basically per time step, right? So how does this work? We have the size per dimension. In this case, it's a quadratic 3D problem space, so every dimension has length L. So we take L times L because we need to exchange this quadratic area here of information. We take this product of L times L times W. That's the amount of data per element that we need to exchange. So whether you're working with floats or with doubles, or think of a more complicated problem where you not only have a single property to exchange, but a range of properties like pressure, temperature, I don't know, the different properties or the different ratios of gases. It could be nitrogen, it could be oxygen, whatever. So it could be more information. At the moment, we're only exchanging a single value. And this again we take times 2 because we need to exchange the information once up and once down, right? So for simplicity, let's just assume a periodic problem space here because that makes things a little bit easier. And if you do that, you end up with 2, because we go up and down, times W, which is the amount of information to exchange, times L squared, because that's the area of the information that we need to exchange. So what are the ups and downs of this approach? The pro of this approach is that this is really easy to implement because you only need to split in one dimension. You can just use send and receive in MPI to exchange, depending on which dimension you choose, even contiguous portions of your array, because it's a closed off area here. And this really reduces management overhead in MPI. This reduces the number of messages to be exchanged to the minimum, and it reduces the amount of code you have to write. The problem with that is that the communication volume, so the amount of data to exchange per time step, does not really decrease when you increase the number of ranks that are involved. So it stays constant. And this is really a problem, because assume that we do a strong scaling experiment and we increase the number of ranks, then the relative amount of the problem per rank to be computed will decrease compared to the overhead that you have. And since the communication volume does not decrease, this is some static overhead. This will not reduce for increasing sizes of ranks. And since this is static, for a really high number of ranks, this will become a limiting factor. This will dominate your Amdahl's law formula, right? So we will try to arrive somehow at a decomposition that also reduces the amount of data to be exchanged once you increase the number of ranks. In order to do that, we can try to switch to the pole decomposition. The pole decomposition is quite similar, except that we now decompose in 2 dimensions, and we sort of build these poles. People also sometimes call it pencils, for example, because it looks like a pencil that you write with. Whatever you want to call it, column maybe, I don't know. The basic principle is simply you just split in a 2nd dimension also. And the question is, what is the effect that we have on this? So we again need to split down 1 full length of our domain, which is L. But in the 2nd domain, because now we are splitting in a 2nd dimension, we can divide L by the square root of n, which is less than we had before, times W again. W because the amount of data did not change. So whether we are exchanging a single double value or a single a double precision value or a single precision value, this doesn't change depending on how we decompose. So the W will always be the same value. And the amount of messages we send is now increased, because once we need to exchange the message going up and down, for example, and then we need another 2 messages for sending the data left and right. So this is why we have 2 plus 2 here. And this is why I wrote it that way, in order for you to know why we arrive at this value. So overall, this is the overall term that you arrive at when using the pole decomposition. And the advantage of this approach is now that, as you see, we have here in the denominator the square root of n, which means our communication volume does decrease with increasing number of ranks, which is a good thing. The downside of this approach is that, however, the surface to volume ratio also increases with n. So the first surface to volume ratio is basically how many messages or how much data you need to exchange compared to how many grid points you compute, right? So the computation of grid points is always 3-dimensional here, because we get either slabs or poles, or in the next example it will be cubes, but you always have 3 dimensions that every rank computes. In this case it's one of these poles. And the amount of data to exchange, the surface, this also increases with increasing numbers of ranks, which is not something we like, but that's just the way it is. And if you extend this approach now to decomposing in all 3 dimensions, what you arrive at are cubes. So we also decompose in the 3rd dimension. And once we do that, we arrive at this formula where, since we split in all dimensions, we divide L by the cube root of n. We do this twice, again multiplied with the W value, because that doesn't change. However, this time we again need to add 2 additional messages, because we also need to send messages to back and front, and not only top and down and bottom and left and right. So in this case also we have a decreasing communication volume for increasing n's, because we have n as the square of the cube root of n in the denominator. But we still have this increase of surface to volume ratio issue that's the same as before. And also, more importantly, we keep increasing the number of messages, right? So now we already have 6 messages. In the previous example, there were 4 messages. And both of these are worse than the slab decomposition we had in the beginning. And now I could tell you lots of stories about, okay, this is good, this is bad, and just trust me that poles is the best decomposition, and for some problems it might be cubes and so on. Really depends. However, this is really easy to compute because they are just simple math formulas. You can just fill in some numbers and see what's going on. So in this figure here, I try to show you the communication volume, so the amount of data to be exchanged per time step. On the bottom you have sort of the legend. That's our bar for the heat maps that we use. So this plot style is called heat maps or hue maps sometimes also. Which is just sort of a 3D plot, and I don't want to use a 3rd dimension, so my 3rd dimension is just represented using a color. It's a really handy visualization for those of you who didn't see this before. And what we have on the x-axis is an increasing amount of problem size. You will see that there are no units here. It's not like kilobytes or gigabytes or something. We don't care about that. We just fill in numbers to the formulas. We don't care about the actual metric or the actual unit at the moment. And on the x-axis, we have the increasing problem size, whereas on the y-axis, we have an increasing number of ranks. And I have three figures because we have the three decompositions we just talked about. For the slab decomposition, you immediately see that we sort of have a vertical pattern because for increasing numbers of ranks, as I told you, the communication volume does not decrease. So even if we really maximize our number of ranks to a really high value, say we have 100,000 ranks or 1,000,000 ranks in our large supercomputer, we always have to exchange the same amount of data, which only depends on the problem size. And this is, of course, bad. If we switch to the pole decomposition, you see that we sort of have this gradient, this inclination of larger number of ranks having a smaller communication volume, right? Because we sort of have this blackish area. I hope video compression and everything is still giving you something in terms of the colors. If this should be a problem, let me know and I can post a screenshot into the chat, but I think with today's technology we should be fine. You can also see it down here that for a really large problem size and a low number of ranks, you really have to exchange a lot of data. But as you start to increase the number of ranks because of the pole decomposition in 2 dimensions, we start to decrease the amount of data to be transferred. And this is really beneficial in the long run because for a large number of ranks, you really do not want to exchange too much data because you will have this going on potentially 1,000,000 times for large supercomputers. And we see the same effect or the same behavior for the cubes decomposition, which is even stronger. As you might be able to see, there's very little difference between those two figures, especially when you compare it to the first one. But you see there's less of a blue area here, and you see that there's a sort of flatter gradient down here when it comes to the pink colors and the yellow colors and so on. And the main takeaway of this figure is that first of all, you should not be fooled by this figure. I keep telling you that slabs is really bad because for a large number of ranks, the communication volume is still constant, is still static, and this is really bad. However, do not forget, this is still a parallel program where you decompose your workload and your data, and you try to use parallelism to speed up your program. So if you have a small number of ranks and you have a very large problem, you probably end up somewhere here, and you might have roughly the same efficiency as poles or cubes, just in terms of the pure amount of communication volume to be exchanged, and you have much less management overhead, you have fewer messages to exchange, you have much easier code to read. So I don't want to put this as slabs is the worst thing that was ever invented, obviously not. There are some problems for which slabs is easily sufficient. And the other way around, poles and cubes are a smarter decomposition for increasing numbers of ranks. So if you write a program with a really high degree of parallelism, you will probably want to switch to one of those two at some point. Although poles might actually outperform cubes in many cases, depending on how much data you need to exchange, just because the additional message overhead of cubes and the additional management overhead of cubes doesn't give you any additional performance gain. But again, it makes the code a little bit more complicated to work with, and you increase the number of messages, which means you increase the latency that you deal with. And you could try to come up with something smart, like using derived data types in order to reduce the amount of messages you need to exchange, because you try to do it you try to aggregate data, but you still need to send messages to individual ranks. So in hardware, unless you have some really smart broadcast hardware topology using InfiniBand or something like that, you will still have to send individual messages. Maybe you don't do it, but MPI will do it for you, but sometimes it can be difficult to sort of mitigate this overhead introduced by the cubes decomposition. But this is just to show you what we hinted on yesterday in the Proseminar, that there are these 3 different ways of decomposing, and there's a real difference in the efficiency and in the amount of data to be exchanged. So far I showed you a lot of examples of how decomposing rectangular problem spaces, which is really interesting, and it's a very nice teaching case because it's really easy to illustrate, right? You just take, I don't know, a rectangular grid and you cut it into slices, you color it in different colors, and that's it. And the cube took a little bit longer to draw, honestly, using PowerPoint, but still it's easy to do. However, I don't want you to think that this is only possible for rectangular problem spaces. Obviously, you can do this with multiple different data structures, not only rectangular or regular ones. So first, I want to show you a very simple illustration of a tree-based data structure where we have leaves of the tree that can be distributed, and those are really easy because you just need some way of addressing leaves in your tree. This could be, for example, if it's a binary tree, just a path that you take. So for the red rank, for example, you would just not specify coordinates in your rectangular grid, but you would say the leaves that you reach when traveling in a path 0, 0, 0 and 0, 0, 1, for example, those are the leaves that should be sent to rank red or to rank 0, whatever, and should be computed by this rank. Or if you're not only dealing with leaves but entire sub-trees, then just specify the path to the sub-tree and everything below will be handled by this rank, right? This is not too difficult. But this is also sort of a data structure that you know to work with, and you might think, okay, maybe there is something more complicated. So just for fun, let's put an elephant up there. And I could tell you that it's really easy to decompose an elephant into different regions. You could just have one rank compute sort of the head and the trunk here. You could have one rank compute the area of the ears. Another rank work on the trunk of the trunk of the elephant, and have the fourth rank work on the feet. And this might sound like a really stupid example because obviously we're not working with elephants in high performance computing, but this is just to show you it doesn't really matter what your data structure looks like. There might be some data structure in whatever you do later on. I know I have at least one PhD student in my course. Depending on what research you do, depending on what company you work with, you might have really complicated data structures, and it's just about figuring out how you can decompose this data structure into smaller parts and how you can address the smaller parts. So for the rectangular grid, it's really easy. We just use coordinates. You've already seen that in MPI you can use subarray by specifying a start and an offset, for example, or a length, and you can address individual subregions of a multidimensional rectangular grid. In a tree, we can just use, for example, the path that leads to certain subtrees or leaves of a tree. And in terms of the elephant, well, I don't know, you would have just to come up with some way of specifying this is the head of the elephant, this is these are the ears of the elephant, this is the trunk, these are the feet. And once you can do that, you need to be able to just send it to a rank, to send this sort of container that holds this data to another rank, and then you can split up your elephant being worked on in parallel. It's really only about how can I decompose my data structure, so how can I split my data structure into individual parts, and how can I address them. And the worst thing that you can always do, so that's the most naive solution, just try to find an enumeration of elements. So at some point I told you, you have to discretize your problem, because computers are always discrete. And once you discretize your problem, you can always do an enumeration of elements. An enumeration might not be the smartest thing to do. Consider the entire tree here, and we want to send the entire tree to a single rank. Enumerating every single node is a lot of overhead compared to just specifying this node and everything below it. That would be this could be a single pointer in your data structure, for example, right? That would be much faster, but enumeration of elements is usually something that you can always do in order to arrive at a decomposed data structure. So sort of closing on this topic, what are the considerations you should take when you do domain decomposition? Well, first of all, how much data do we have to transfer? I hinted at this with enough figures now, I think. Just consider the amount of information you need to transfer, the amount of data, and you will be bandwidth limited to some degree in the sense that you can't increase this bandwidth. You can change your rank core mappings in order for data not to exchanged over the network, but only over memory links or only over links that connect CPUs. Or if you work with accelerators, for example, why not send data over the PCI Express bus? But all these links have a hard-coded, because in hardware, bandwidth that you cannot exceed, so we need to be careful with that. The second thing is, how many messages can we reduce this to in order to transfer the data? Any additional message usually incurs additional latency overhead unless you use some broadcasting mechanism and have a really smart hardware means of connecting nodes, for example, but you can't assume that you do most of the time. Additional messages don't only mean additional latency, but you also need additional buffers, which increases the memory footprint, and also it increases the management overhead inside MPI, because there's just more stuff to deal with. And usually additional messages also just mean additional code. You could just outline it to functions. We saw Marcus optimizing this yesterday, for example, but there are only so many things that you can do here. Another thing to worry about is the cache efficiency of the decomposition. This might only be an implementation issue, so depending on what your algorithm looks like, on paper you might not be worried about the cache efficiency, but only when implementing it, for example by switching between rows and columns. We also discussed this a little bit yesterday. And otherwise it also makes sense to have a decomposition, for example, that is sort of recursive by splitting into smaller, increasingly smaller parts. I will show this a little bit later with figures, that try to cover as much data as possible in the least distance, sort of to speak, possible, in order to increase the cache efficiency. So when you send data to one rank that has that's working on a core with a cache connected, you try to put as much data into this cache as needed by the rank, but not more, and especially not data that will not be used by this rank or not used too often. So we can talk about data reuse and cache efficiency of algorithms maybe in a later lecture, but the idea is just to keep the decomposition sort of structure, the geometric forms of a decomposition, as compact as possible. And well, the last thing is how complicated really is the implementation. So you might be able to come up with a decomposition scheme that is extremely efficient and gives you 2% performance increase over your existing solution, but you require double the amount of code for it, which might decrease the readability, for example, to 50%, whatever readability means. So quantifying code readability, quantifying code complexity is quite problematic topic, because it's a very subjective metric, not really a neutral one, an objective one. Just worry about the thing that I keep telling you. Don't make it overly complicated, and think about when you have to reread code in 1 year from now, was it really worth the effort in order to get the small performance increase? However, the two most important considerations that you should always stick with before dealing with any of the other issues are: can your domain actually be decomposed efficiently? Is it possible for you to do this efficiently, for example, not resorting to enumerating individual elements or drawing really strange lines through your problem domain? If you think that you cannot come up with a decomposition that is efficient and effective and does exactly what you want with a minimum amount of overhead, consider whether your algorithm is actually the correct choice. Consider whether you want to change your algorithm into something else. Similarly, if you have a data structure that cannot be decomposed efficiently, especially, for example, if you need to resort to enumerating elements, consider changing your implementation. So don't use a contiguous array, for example, if you can also use a linked list, which is much easier to decompose because you just sever pointers, right? Contiguous arrays, you might need to copy, you might need to split. If you need to insert data, it's an expensive operation because you need to move data and so on. Linked lists are more efficient in these operations. So this really depends on how you want to decompose your data structure, what operations do you need in order to decompose your data structure, and then you choose the kind of data structure you use, whether it's a bag or a set or a linked list or a tree or whatever you need. And most importantly, I already told you about this, try to figure these things out before you start coding. Usually, of course, you think you have a smart solution, you start coding, you do some measurements, and then you figure out, okay, this is not as fast as I had hoped. You go back to a drawing board and you figure out a smarter solution, and then you need to change your implementation. But don't just go ahead and just start implementing without thinking about these topics just a little bit, because that will usually save you time if you do that. Okay. So far, I don't see any questions in the chat, so I hope you're fine with the content so far, and I hope the stream and the audio is still working. In that case, let's continue with load imbalance. Otherwise, just stop me in between. So load imbalance. Actually, I have a question from Marcus. A question regarding the two heat stencil. Isn't it the case that we always have to send the same amount of data in total per time step? If the communication volume is smaller, we need to exchange more messages, right? No, if you do that, In the 2D heat stencil, I didn't know. Also in the 2D heat stencil, I think it doesn't hold. If you do the computation for the 3D heat stencil, it definitely doesn't. For the 2D heat stencil, I would have to probably get a pen and paper and draw it now to be sure. But if you do the computation, you figure out that actually in 3D it's less, which seems counterintuitive, but that's really because otherwise you can end up with really strange decompositions. I will show you figure at the very end of the lecture which deals with space filling curves, which shows you a really strange decomposition, and then it really starts to matter how you distribute or how you decompose your data. You could also think of it like that. You could arrive at the same volume of an object no matter whether it's a cubic, a cube really, or a cuboid that is just one in one dimension and really long in the other dimensions, for example. Like a really flat object or a cube that is as compact as possible. You can have objects that have the same volume but different surface in that regard. And that's why the amount of data to be exchanged differs. If you can read up on this, you can also just try to do some computation on pen and paper, and you will see that there are different numbers actually, although it's a little bit counterintuitive. Okay, load imbalance. So load imbalance, I already told you, refers to the phenomenon of not all ranks finishing at the same time. This could be, in general, load imbalance can be caused by ranks not finishing at the same time because they have different amounts of work to be done. They have to wait for other ranks because your communication is sort of imbalanced. Some ranks might be idling for some other reason because they have to work for, they have to wait for the hard disk, and your I/O subsystem is not as fast as you want it to be. In any case, you arrive at something that looks like the figure on the right, where you have ranks finishing not at the same time, for whatever reason. Now there are two different types of load imbalance. Load imbalance can be static and load imbalance can be dynamic. Static load imbalance is caused by, or is load imbalance caused by initial conditions. Say for example, we have a weather prediction simulation where we want to do a weather prediction for Austria for today in the afternoon, 3 p.m. for example. And you just do a regular rectangular grid, equidistant grid, which means all the points have the same distance, all the cells have equal size, and you lay this grid over Austria, then you have a lot of mountains in Tyrol, for example, in one cell, and sort of a plain area, for example, in Lower Austria or in Vienna, in some other cells. You still have sort of the same area as in a top-down view, but mountains are a much more complicated topology because you can have föhn, for example, you can have turbulent areas with winds that go the other direction of the main wind direction that sort of blows over Austria, and this really makes weather prediction more complicated, and you need to increase the amount of work to be done for these complex topology regions, because otherwise you arrive at really bad results. So if you take the same resolution for Vienna or Lower Austria, for example, and for Tyrol, then your weather prediction might be really accurate for the east end of Austria, and it might be really bad and really inaccurate for the west end of Austria. So this is when we need to sort of change the amount of work we do per cell, and we arrive at load imbalance. However, this doesn't really change throughout the simulation. This is really an initial condition because the topology, the mountains do not change, at least they don't change that fast. Another example would be, for example, doing oil spill simulation, which is something we did. If you remember, I told you that we did research in that area, and you have a more complicated math behind simulating how oil behaves once you're at the ocean shore, because you have tumbling waves, for example, which you do not have in the open sea. So for the open sea, it might be easier to compute. On the other hand, it might be, depending on what you do, exactly the other way around, because the open sea has a much greater depth, for example. You can go down to, say, 11 kilometers if you go for the for one of the abyssals. And if you're at the ocean shore, you have a much shallower water, which, depending on your actual problem, your physics simulation, might induce less work. Who knows what you want to do. And it could be as simple as the remainder in an integer division, for example. In the example so far, we said that we don't need to worry about that. Just if it's not evenly divisible, give the user an error message and don't hide errors, silently. But if you do need to worry about that, you end up with some ranks that have more chunks than other ranks, and this is a simple result of of problem domains that are not evenly divisible by integer division, and you end up with remainders. For all of these cases, and you can come up with many more examples, this does not change during the application execution. So this is something that you should deal with at the beginning when you do your initial overhead. When you read in data, you might need to read in data at a single rank and then do some redistribution, or you might already be able to generate the initial data and sort of mitigate this load imbalance at the start, but this usually doesn't incur any runtime overhead afterwards. Contrary to that is dynamic load imbalance. So dynamic load imbalance is something caused by the application data, caused by the application while it's executing. And examples for that are like the Lagrangian simulations that I showed you before, moving particles. For example, say galaxy clusters. You have simulations that deal with how galaxies are colliding, how you have this dynamic friction of galaxies that sort of make each other slower and have a gravitational effect. At the moment, we're colliding with the neighboring galaxies at, I think, 600 kilometers per second. Obviously, we don't notice because of the orders of magnitude and so on, but still, simulating this will incur load imbalance, because if you simulate this over millions of years, the position of galaxies, the position of the stars in the galaxies will change, and you will move these particles. You will move your stars, you will move your solar systems, for example. Another example where you can have load imbalance without moving particles, for example, would be partial availability of sensor data. So whenever you do simulations like the oil spill thing that we did, you might have the math figured out, you might implement everything, and then you do the simulation. And while you run your simulation, you just watch the news and you figure out, hey, there's a change in the conditions that I did not foresee, that isn't really part of my simulation. So it would be really nice if I could just incorporate this information while my application is running. This is there are several methods that can be used by that. For some of you who know a little bit more about math, there's a thing called Kalman filtering that allows you to sort of converge to data that has been measured with your simulation. So basically this means I do my simulation, and whenever I get measurement data, I include the measurement data compared to the simulation data at the same location where I got the measurements, and see if I'm off by some error, and if yes, I try to correct with the measured data in order to improve the overall accuracy of my simulation. You could also do this with forest fires, for example. So there are lots of disposable sensors that can be ejected from a helicopter, for example, and they just measure temperatures, they measure gas composition and so on. And when you want to simulate how forest fires are progressing, you can try to include this kind of sensor data in order to get a more accurate location of where you want to send fire brigades, for example. And this is something that can work also with a fixed grid. So this has no moving particles. This just depends on where do I have sensor data and when do I have this sensor data available. And the last thing is you could have also, for example, a fixed grid, and each cell could differ in the amount of work because of the convergence of iterative algorithms. Assume that for every cell you need to solve, say, a set of partial differential equations or something like that, and usually what you do is you do iterative approaching, you iteratively approach a solution, and depending on the data at this cell, it might take you a different amount of, or varying amount of iterations in order to arrive at the result. If this is the case, it could be that on one grid cell it takes you 100 iterations, and on the adjacent grid cell it takes you 100,000 iterations to get the result that you need. This is of course load imbalance, because then one cell doesn't equal the other in terms of workload. And the important thing about this dynamic load imbalance thing is that this really changes during the execution of an application. I hope these examples sort of illustrated that. And because it changes during the execution of the application, it requires rebalancing. So that really means you need to, for example, rebalance at fixed intervals, say every 10 time step iterations of your time loop, if you have something like a time loop. You need to do a rebalancing, or at least you need to check if you have load imbalance. You could also say you just do that whenever you reach certain limits. So just do an instrumentation of the execution time of every rank and take the time step of when they finish, and you always compare. And if they are, if the finishing time steps are, the difference is below, say 1 second, you don't care. If it exceeds 1 second, you start to rebalance, because rebalancing always incurs some kind of runtime overhead. You not only need to exchange messages in order to, for example, send data around or change the decomposition of your workload, you also need to have the management code that actually figures out that this is necessary. And all of this is overhead that you, most of the time, you do not want. So this is really a trade-off between being able to rebalance a lot of the time or most of the time and having a huge overhead because of that, or not balancing that often, but then accepting some load imbalance before you actually deal with it. The bad news reloaded, MPI doesn't offer any capability of doing load balancing for you. Yes, you have low-level functions like MPI scatter V, where you can do load balancing by sending different amounts of data, for example, to different ranks, but again, it's only the underlying tool. You really have to do this yourself. And again, there are certain domain-specific languages and libraries that try to do this automatically. They are the same ones that I mentioned before and that I will introduce in one of the last lectures of this semester, but none of them are really at a level where you just take it, you just program your application and you run it on a supercomputer and it just works out of the box the same way OpenMP does, for example. But OpenMP then again doesn't offer load balancing, at least not for more complicated problems. Okay, so coming back to a specific example, which is the space weather prediction that I showed in the first lecture, I believe, because this is one of these dynamic codes that can have dynamic load imbalance because it deals with moving particles. And it's called particle in cell, this kind of code, because you actually have particles that move around in a grid, and you need to deal with both the grid that you have and with the moving particles. I will show an illustration on the next slide. And just to reiterate on what this application is actually doing, you have charged particles coming from our sun, from our star, which can be electrons, protons, alpha particles, and so on, and they hit the Earth's magnetosphere and are deflected, which sort of should be illustrated in this artist's illustration on the left. Which is a good thing because, and also on the right, you see that once you approach the Earth, you have fewer particles, and the artist tried to show some particles that, you know, flying away because of the magnetic field that is illustrated with these field lines. And this is a good thing that we have this magnetic field, because that basically protects us from these solar winds. And once the magnetic field gets a little bit less intensive, or the solar winds get more intensive, you really have an impact. I think I showed you an example in, was it 1989 or something, we had a power outage in North America sometime in the 18th or 19th, I think it was 1860 or something. People were just communicating over telegraph lines, and a solar wind was so strong that happened back then. It actually induced a current in the telegraph lines that paper at the end of the telegraph machine started burning, and people got an electric shock. And nowadays our electronics are much more fragile, so if something like that happened again, it's possible that, for example, cell phones might break. And we have to worry about satellites, which are not on the surface, obviously, of the Earth, but in low or medium or high Earth orbit, whatever. And they, as the height of the sort of the flying height of the satellites increases, they are more exposed to the elements of our universe, and this can be a problem. This is why we do this sort of simulation, to figure out how strong does it get, which areas on Earth would be more exposed, or which satellites, depending on their orbit, how well protected do they need to be, because you don't want to send up kilograms of protection material that you don't need, because every kilogram costs a lot of money, and so on. So how does this simulation work, this kind of particle in cell simulation? You have charged particles illustrated here on the right with these orange circles that are moving at different velocities. They all have a different position. They're moving in sort of any direction. And they move in an electromagnetic field that is sort of represented by this blue grid here. And since the particles are charged and they're moving, they again themselves affect the electromagnetic field and are affected by the field, vice versa. So what you do in this kind of simulation, one of the ways of solving this is to just in every time step, in the first step you move the particles. After you move the particles, you again solve the equations that govern the electromagnetic field in order to get the different field values. And then you do the next time step and you again move the particles, you solve the field, you move the particles, you solve the field. And the field has defined grid points just with our stencil that we had so far. This doesn't change, but the particles are moving, and they can move from one cell to another. And if the particle moves from a cell on one rank to a cell on another rank, you actually need to send the data of this particle over the network, right? And this is something that we have to deal with. So there are several different sort of use cases depending on the input data that these particle in cell cases can have. I illustrated, I think, 4 cases in total that are sort of picture book examples, and try to show you the difference between the static and the load balance on a specific example that really could look like that when you do galaxy cluster simulations, for example. First of all, let's discuss a uniform distribution. So you see a three-dimensional domain with the particles distributed, and you see two positions here, so actually twice as many points as we have particles. The blue dots represent the initial position of every particle, and the orange dots are the final position of the particles. And it's not that well visible. I don't know what it is, but there is very little movement in this. So this is actual data. This is not something that I just drew up here or something. This is something that we actually ran simulations with. I first will tell you what this looks like and what load imbalance this incurs, and afterwards you're going to see performance data gathered from this exact input data running on LCC2. So in this case, we have a sort of uniform distribution through our entire problem space, both statically in terms of the initial position, and also the particles don't move that much. Which means we do have very little static load imbalance because the particles are sort of uniformly distributed, right? There's very little difference depending on whether you're at the center or at the borders, for example. It might look a little bit different here, but that's just a visualization thing because it's a 2D view, and if you cut through the cube at this position, you have less distance to go through the cube compared to the center here. It's just a different length of the diagonals. So this is really uniformly distributed. And you also have very little dynamic load imbalance because the particles stay almost at the same position. And even if they change around a little bit by one particle traveling to another rank, for example, other particles might or travel the other way around, so it will sort of cancel each other out, all of these movements. The next use case is the cluster use case, where we do not have a uniform distribution, but a normal distribution that's centered around the center. So we have a large amount of particles, or a large particle density rather, at the center, and a decreasing density once we move towards the edges of our cube here. This does have static load imbalance because the particles are no longer uniformly distributed, right? So ranks working on same sized cubes at the center have more particles to work with compared to the border of your entire problem domain. But again, the particles do not move that much, so there's very little dynamic load imbalance. The load imbalance doesn't really change, it stays constant. So if we have something like this, we could just split our domain in cuboids that don't have equal size, and we don't need to change throughout the run of our simulation. The next use case is explosion, where it's sort of barely visible. I hope this is visible in the video stream, I guess so. We have the initial position of the particles, which are sort of packed together into a ball of particles. This could be, for example, sort of the birth of a galaxy. If you go for smaller scales, this could be the explosion of a supernova or something. With the initial position initial positions being packed together very tightly, and throughout the simulation, the particles will sort of spread out in our explosion and arrive at the sort of normal distribution that extends up to the edges of our cube. In this case, we have both static and dynamic load imbalance, right? Because static load imbalance of the initial distribution of the particles, and dynamic because it will change. Even if we split our domain only considering the very center where we have the particles, after some simulation steps, we will have ranks on the outside that suddenly need to deal with particles that they didn't have to deal with at the beginning of the simulation, and this is dynamic load imbalance, so we might need to shift this during simulation run. And then we have a stress test case, which is really the worst in terms of how to deal with this. Consider, for example, an electron beam that shoots a high number of particles from one corner of our problem space to another corner of our problem space. This could also be, for example, a large, relatively empty space where you have a solar system traveling through, or a galaxy or something, with very little material or particles in between. And this is really the stress test of all of them, because we have all the particles packed together at almost the same position, and they will move throughout our problem domain during the simulation. Some ranks will never have to do any work at any other position, and those ranks at the diagonal will have to do work in a serial fashion, in the sense first the rank with the first cube, then the next cube along the diagonal, and so on and so on. And this is a static and dynamic load imbalance as much as possible, because most of the ranks do not have to do any work throughout any point of the simulation. And as I said, this was a stress test for our framework that we did. All of these things that I'm presenting you was part of the all-scale project, and I'm going to show you some visualization later on to show you how we worked with that. But it's not necessarily only a stress test. You could really encounter something like that. So most of the time, you do not have to care about this because your input data will never have such a strange sort of synthetic distribution, but you really need to be sure. And if you figure out a domain decomposition that can work perfectly with a case like this, for example, at some point you then get input data that really looks like this, you still get bad performance, although you do have load balancing, but you never considered it can be as extreme as this case. So you always need to know your application. You always need to be aware of the potential input data you can get. Now, I told you I measured this. To show you that I'm not just coming up with funny pictures and claiming that this has good or bad performance, let's look at some actual numbers. So this is the performance of the IPIC 3D code, all 4 use cases done with strong scaling experiments. So I started with 1 million particles on a single core, and I scaled up from a single core to 8 cores on a single node, and then moving up to additional loads up to 64, as we also did in the last Proseminar. And this is data really gathered on LCC2. I ran the experiments last year, but I guess the performance wouldn't change. So what can we see here? First of all, when we look at the speed up, we see that the uniform distribution has the highest speed up for the maximum number of cores. So for 64 cores, we arrive at a speed up of 40. This is quite simply explained by the fact that this is the easiest case, right? So, and I should add, in this case, in all scale, we did some research in how to do automatic load balancing, but because I want to show the effect of these things, in this case, there was no load balancing, the component was disabled, which means we just run the simulation with equally sized numbers of particles, so equal numbers of particles, and we just see what's the performance that we get. And in this case, you see the uniform distribution has the highest speed up because the particles are uniformly distributed. There's no static, no dynamic load imbalance. We can easily work with that, right? A speed up of 40 for 64 cores. Well, it's not 64. It's definitely not super linear, but it's okay. It could be worse. We see here on the efficiency plot on the right, it's an efficiency of just above 60% here. And I didn't do any specific optimization here. This was just run out of the box. So for cluster, which was the thing where we had static load imbalance because of a normal distribution rather than a uniform distribution, but the particles do not change much throughout the run of the simulation. We have static load imbalance, but no dynamic load imbalance. And you can see the performance is definitely worse. So we get a speed above 15 or so for 64 cores, which is an efficiency of just above 20%. It's much worse than uniform, but it's still not nothing. We still get some sort of speed up. Now switching to the special cases where we have our explosion with also dynamic load imbalance, sort of the same as cluster, but includes dynamic load imbalance, and then beam, which is our stress test. First of all, you notice there are no data points for 16, 32, and 64 cores. Now, why is this the case? No, Philip was not too lazy to run it. The problem is that these already, without any load balancing, scale so badly that at 16 cores and more, we got a runtime of more than a factor of 10 or a factor of 20 of the runtime with 8 cores. So I just stopped the simulation there. I had a hard limit of maybe an hour of the overall simulation. I can't remember exactly, but had a cutoff in the sense that if it takes more than a factor of 10 or something of the previous point, I will just stop the simulation because it doesn't make sense. Why do we see the split between 8 and 16? Well, it's easily explained. Among 1 core through 8 cores, the data points were gathered on the same node, which means we have comparatively fast communication because we communicate over the memory. We have just in-memory communication. When moving from 8 to 16, that's the first time I need to start to use the network. And the network, although LCC2, it's old, but it had a comparatively fast network for the time. And it's still faster than gigabit Ethernet or something like that. It's still orders of magnitude slower than communication over the memory bus, both in terms of the bandwidth as well as the latency. And we see that here, we see the direct evidence because already the case with 2 nodes for explosion and beam, the execution time took so long, it was more than a factor of 10 or a factor of 20 or whatever my cutoff factor was, that the jobs were killed. And it didn't make sense, obviously, to run it for anything higher than that. that's the one thing you can see. The other thing you can see that explosion still scales sort of well up to 8 cores, and beam doesn't. Because with explosion, although we do have static and dynamic load imbalance, the particles are still spread over a larger number of grid cells compared to beam, where all the particles were actually in a single cell and traveling throughout our problem domain, almost sticking to a single cell. Only when you arrive at the corners, they might end up in 8 or so different cubes, but once they start traveling a little bit further, they are again just in a single cell. If you think about the 3D geometry, I hope that explanation makes sense. So, although it also does not scale to 2 nodes, it already scales much worse for a single node, and we basically do not see any speed up here. I don't have any absolute numbers here, but you can see a little bit more here in the efficiency plot, where we see that the efficiency for 8 cores is already down to below 20%, so probably 15% or so. And explosion can hold an efficiency of 70, 72, 3, whatever percent, although they both have dynamic load imbalance. And this should show you just how bad something like dynamic load imbalance can be if you do not deal with it. And static load imbalance also, although you do see the difference. So static load imbalance is something that usually you can more easily deal with because it's just the initial distribution, and it really takes some management overhead to design a data structure that can accommodate changes during the runtime. Because you need to maybe reallocate data, you need to use reuse lists for chunks of memory space that you want to use, and so on and so on. So being able to do this dynamically at runtime really blows up the complexity of your data structure, which is why you don't want to deal with if you don't have to. But as I showed you in these examples, unfortunately there are cases where you have to. Load imbalance can be detected with tools. So on the right you see a screenshot of just one of these tools. In this case it's the Intel Thread Analyzer, Intel Trace Analyzer, I'm sorry. There's also a tool called Thread Analyzer. What you see here is the execution of the mini FE benchmark of the Sandia National Labs. So FE stands for finite elements, which is essentially just a stencil application. And this was run not only on CPUs but also on accelerators. So what you see here are lines 1, 4, 7 and 12. Those are the lines where they ran on CPUs, ranks that were run on CPUs. And the ranks in between, the other lines, line 2 and 3 and so on, are lines with ranks that ran on an accelerator, specifically in this case on a Xeon Phi system. So this figure is probably already a few years old, but it doesn't change the principle about dynamic load. The blue bars you see is time, or are time spent in user code, in actual useful computation. So this is just a small excerpt. You see that we have a scroll bar here with a really small knob here, which means that's a quite detailed view of the overall runtime. The overall runtime was probably around 70 seconds or so. And here on the top you sort of see the time of the x-axis, but I can barely read it, so probably you in a video stream can't read it either. In any case, you see time progressing from the left to the right, and blue bars are actual useful time that's spent in computation. It's annotated here with user code, if you can read that. And the red bars here are time spent in MPI communication or synchronization. So in this case it was an all reduce, which is a quite expensive operation, because not only is it global, it's a collective operation, so everybody needs to participate. That's why you see all of the ranks sort of syncing up at the same vertical lines here. But also it's an all reduce, which means the final result needs to be communicated to everybody. And what you see here is a picture-perfect example of load imbalance, which is why I took this screenshot. So you have user code on the CPUs finishing in a certain amount of time, and sort of the same user code here run on the Xeon Phi finishing in half the time. And for the remaining time, the Xeon Phis are just waiting for the MPI all reduced to finish, which can only finish once the CPUs finish their computation and are also ready for the communication operation. So this time of the Xeon Phis here is just wasted. They are just waiting when are the others ready. They're just blocking until the all reduce finished, and they could do some useful computation if you end up with different sized chunks between the CPUs and the accelerators, because the accelerators are much faster. So far I only talked about load imbalance caused by different amount of work for the different processing elements. I have a summary slide later that details a little bit more on the fact that You can also, of course, have load imbalance if you use heterogeneous systems, and in this case, you use a system with accelerators that are much faster than CPUs, and you should be able to deal with that, because otherwise, half of the productive time of your accelerators is just wasted, right? And there are tools that can nicely show this, and we're gonna discuss performance tools a little bit later in the semester, as I mentioned. Now, how do we deal with load imbalance in general? Well, first of all, you need to be able to quantify the amount of work of any sub-range of your domain. For our heat stencil, for example, in 1D, it's really easy. Then it's just the number of elements, and the number of elements is computed by subtracting the end index with the start index, and then you arrive at the number of elements. It could be some more complex data structure, and then you might need to hold meta information, where you do not only then transfer data to a certain rank, for example, but also you transfer metadata that tells the rank how much information you think, how much work you think this chunk is, and then the rank can decide on whether it should be further splitted, for example, among the cores, if you do a hybrid programming model with OpenMP threads for the rank, and so on and so on. So at some point, you probably need to start to compute how much data is there and how much work is it. And you can't just take the number of elements for that. Then you should choose a domain decomposition scheme that allows to split the workload in even shares, and if required, rebalance the workload during the runtime. This is also something that many domains call adaptive refinement. For example, you end up with a grid that can be cut into smaller pieces. I have figures on the upcoming slides. And in general, if you deal with a black box problem, if you don't know exactly what is being computed, you can, for example, change the chunk size, but you don't really know how much workload one chunk is, because you don't really know what is being computed. Then you just have a general trade-off. OpenMP offers this, for example. OpenMP offers loop scaling policies, dynamic and guided, which can deal with load imbalance. But OpenMP doesn't know anything about how much work a single iteration of a loop is. So it's just doing this at runtime, dividing in chunks and assigning chunks at runtime. And there you just have the trade-off, as we discussed before, do many small chunks, then you can easily mitigate any load imbalance, but you have increased management overhead because you have more chunks to deal with. Or you have fewer chunks that are larger, then you have little overhead, but it's more difficult to balance the load because you are not as fine granular as you would need to be for dealing properly with the load imbalance, for example. And you should also note that decomposition itself is also overhead. So decomposing a problem space obviously doesn't come for free. It's also something we need to deal with. Now, different approaches of doing load imbalance, you can sort of classify them in many different ways. One way of looking at this is whether you do it reactively or predictively. So reactively means I monitor the system state, and as soon as I detect that there's load imbalance, I try to mitigate this. And obviously this means you need to monitor the system state, you need to take time measurements, you need to check when do ranks finish, for example, and then you need to aggregate the information to some ranks or spread throughout the entire system, because every rank knowing when they finished is not sufficient. They need to know when did everybody else finish in order to know whether they went fast or they went slow. So that's information that needs to be exchanged. So monitoring stuff like that really induces overhead. The second approach you could do is try to build a model that predicts the performance and predicts the load imbalance of your system, and then you query the state of your system in your model for a future time point, for example, and you try to shift workload even before imbalance occurs. And there's a huge amount of research dedicated to this field, to building performance models, building imbalance models that first of all try to find approaches of mitigating this load imbalance, try to sort of analytically grasp how this is behaving, and then second, once you have this, not only be able to come up with such a model, but come up with such a model automatically without any user intervention, which is sort of the holy grail of HPC. You want to build a performance model and you want to know how fast this application will be without even running it. If we were able to solve the halting problem and solve NP hard problems, then this wouldn't be any issue. Unfortunately, that's not the case. Otherwise, NP hard problems wouldn't be such a huge topic. And this is why we don't have that, and we usually refer to something stochastic. People like to use regressions for that. They try to build AI models for that, and so on and so on. So yeah, this is ongoing research. In case you're ever interested in following up with with a PhD or something in computer science, there's a lot that could be done here. Now, some illustrations on dealing with load imbalance, both the static and the dynamic case, to show you how this redistribution and adaptive refinement works. You first just choose a domain decomposition that sort of works for your predicted workload, and you just execute as normal. You don't need to do any switching because we have static load imbalance in this case. And on the right, you see what this could look like. In this case, it's a quad tree, right? We have a two-dimensional problem space that we divide into smaller pieces depending on the amount of work. So if this is a quad tree that's sort of bounding particles in a 2D space, it would mean that the squares on the top left and bottom right have very few particles, and the smaller squares here have a higher count of particles. And again, the color denotes a potential distribution among the ranks that you have. The more work you just have at some geometric region, the finer grained you make your subregions that you have. And this can also be done in 3D, obviously. Then it's an octree, not a quad tree anymore. And in general, because this is only one way of doing it, these geometric shapes and structures, how to decompose domains, are called bounding volume hierarchies, where you try to establish most of the time a sort of a tree-like data structure that tries to very quickly allow you to navigate the physical domain that you have, and sort of group the amount of work into geometric shapes that are of different size. But again, the size of the shape doesn't really matter to us. It really matters how much work is induced by that. In this case, the number of particles. Now that's static only, but we can also do the same for dynamic load imbalance. In this case, we just have the same data structure, but it's a data structure that allows us to shift the granularity. And for example, here we have particles that might have been there might have been a lot of particles in the top right corner at a certain time point x, and at time t x plus 1, the number of particles decreased in this code region, in this problem region. So we just merge all of these together into a single square in order to reduce the overhead of management, because then we need to deal with fewer chunks overall. And also, if these were distributed to different ranks, as shown here, because we have the red rank working on one of these tiles and the other 3 being worked on by the blue rank, we can just assign everything to the blue rank in order to make sure that everybody has sort of the same amount of work. But other regions, for example, might be just reassigned to different ranks. In this case, these tiles were black, now they're blue, they're red. And on the bottom right, we further decompose the tile into smaller pieces because of an increasing number of particles. So it could be that we had particles up here that moved to the bottom right corner, and then we have this decomposition here. And doing this requires you to, for example, check at certain intervals what's going on. It requires you to do this when you reach certain threshold, as I said, depends on your actual problem and how much load imbalance you can actually endure. And this usually requires some form of worker queues or work stealing. I will have some slides later on how these systems work. You just need to be able to reassign work on the run. And this is more easily done for shared memory parallelism, because you work in the same memory anyway, and is a little bit more difficult for distributed memory, because you need to exchange messages, of course. Here I want to show a small video of this actually happening in action. What you see here is our all-scale dashboard, which is sort of a task manager for a distributed memory system. And at the moment we have 6 nodes online, which are colored in different colors here. And at the bottom right, you see such decomposition graph. You see that we have a 2-dimensional domain, and we have individual chunks in our 2-dimensional domain that have different sizes, and they are colored depending on what node is currently computing them. So you see all the red chunks, for example, are computed by node number 5, and they are spread throughout your physical domain, which sort of doesn't make sense, because you have additional, for every additional chunk, you have additional border cells, you have additional, you increase the communication volume that you have, because you have more neighboring cells that would be necessary, because these are not densely packed, right? And this is the case because at the moment we selected the random scheduler. And what you can see is, if we continue the run of this video, we will start to see speed and efficiency graphs going from 0 to 100. progressing over time, and we sort of see that the speed and the efficiency are both very low. So this is a very stupid way. You can even see doing random for a longer amount of time is a very bad way of doing it, because you really have lots of ghost cell exchanges, lots of communication going on. Now, if we switch from the random scheduler, which is just doing something or anything, to the uniform distribution, which means the scheduler is trying to aggregate blocks together, you will see that as time progresses, the scheduler not only tries to merge blocks together, but it also tries to assign them to nodes that get blocks that are sort of close together. So we don't have node 5 working on one block in one corner and one block in the other corner. No, node 5 is only working on blocks in this corner, and node 0 is only working on blocks in this corner. And you can also see that the efficiency and the speed up are going up, because we have less communication overhead going on. And the video, now we change to the balance scheduler. There might still be some smaller changes in here, but in general, the main image stays like that we have much fewer boxes. And you might now think that, okay, this is quite obvious. I mean, something that we saw before, let me go back to the random scheduler, something like this is really stupid. Why would you ever do it like that? Please consider this is a very simple 2D examples where you can visualize that. Assume now that you have a 6-dimensional rectangular grid. It's no longer that easy to see. And it might not even be a rectangular grid. It might be a tree, it might be an elephant, it might be something else. So figuring something like that out for more difficult problem domains, for more difficult data structures, is a really, really complex problem. You need really sophisticated systems for doing that, especially if you can't visualize them in 2D anymore. Unfortunately, this video is not part of the PDF, obviously, because that doesn't work. I tried, but Acrobat integrates this video as a embedded Flash in a PDF, and I really don't want to embed Flash anywhere in 2020. So, unfortunately, you don't have this video in the PDF. Okay. Final thing I want to say here is that when you deal with load imbalance, try to incorporate also domain-specific knowledge that you might have access to. Don't make your life more complex and more difficult than it has to be. Often you will have a problem that has some sort of structure that has a direct impact on the workload, and you can use this information to get a smarter decomposition and distribution. So for example, on the bottom left you see source code. That happens frequently in linear algebra. We have an outer loop that iterates from 0 to n, nothing too fancy here, and we have an inner loop that iterates from 0 to I, which means the number of iterations of the innermost loop depends on the current iteration of the outermost loop, and you will end up with some sort of triangular shape. So triangular LU decomposition matrix solvers, for example, or stuff like that, they might have code that looks like this. And if you know that this is the case, if you know the code is not going to change, this linear algebra method is always going to look like that, and you need to parallelize it, then please use this information to come up with a smarter distribution. You could just throw OpenMP dynamic scheduling at this, or guided scheduling, and it will do definitely do a better job than just static scheduling if, for example, you only parallelize the outermost loop. Because every iteration I will not have the same amount of work, because the number of iterations j inside differs. For this, we can even assume that the workload of each j iteration has the same amount of work, because we have different amount of work for I depending on the number of j iterations we have, right? And if you know something like that is happening, then try to decompose the workload in the following, for example, by doing exponential or logarithmic decrease of the amount of work, which is something that guided scheduling, for example, in OpenMP is doing. Why? Because people were doing lots of linear algebra already back in the time. So guided scheduling will do something that's very similar to the shapes that you see here. And the area of the shapes here basically denotes the amount of work, assuming that every j iteration takes the same amount of time. And the general takeaway here is just, if you have access to information like that, please use it. Don't make it overly generic and overly complicated. If you know that this is what the code looks like and it will never change, it will always stay like that, then don't rely on something too stupid like dynamic load scheduling, for example, if you can do something smarter because you already know the amount of work entailed by every iteration of the outer loop. Okay. I showed you basically, I don't know if you noticed, but I showed you examples of, and I'm flickering because AI is not as smart as it should be. I showed you ways of dealing with load imbalance in order to sort of balance out the execution time of every rank in order to arrive at the minimum execution time. This is one thing you can do. So you can use strategies that sort of try to do a smart work assignment. You can just divide into chunks and assign the work in a round robin fashion. You can divide into chunks and assign them in a random order, and you would be surprised how often random scheduling is a really efficient method by just assigning randomly and having the random nature or pseudo-random nature of numbers make up for any load imbalance introduced by having sort of regions in your problem domain that are more work heavy. So people often use the random scheduler because it's much better than some static scheduling, and it just works very well. Or you could use something more complicated, like you could use space filling curves, you could use diffusion models, and so on and so on. There's lots of research going on here. I have one figure on space filling curves, I think on the next slide, I'm not sure. But other than that, I'm not going into too much detail on that because there's lots of stuff happening there. Also very complicated. And usually it's always an overhead between how much balance do you really need and how big of an overhead are you willing to take. But again, this is for minimizing time, and this might not necessarily, or maximizing performance, and this might not necessarily be what you're going for. You could also take a look from another perspective and say, okay, I have load imbalance. I don't care when the program finishes the entire computation, but I could also, for example, clock down certain CPU cores that are that finished sooner with the workload in order just to save overall power and energy consumption. Or not only clock down CPU cores, but switch off hardware, doing power gating, for example, for cores that finish early. If I know that they won't be needed for the next 100 milliseconds, well, I just switch off that core and I save all the power that would be required. Obviously, this doesn't reduce any wall time, but it saves you power and energy, and there are people who really do this, because for large supercomputing centers, this can really make a difference in the order of kilowatts, for example. So, or even megawatts if you use the entire system, although that's a little bit unlikely. And people do this, for example, there's a lot of research that's already 10 or 15 years old where people try to save power by checking when is my program in MPI communication and when am I just busy waiting for MPI communication to happen, which were the red bars in the Intel trace analyzer that I showed you before. And whenever you reach one of the red bars, you just clock down to the minimum frequency, and once the communication finished, you clock back up. If clocking down and clocking back up is fast enough, then you save a lot of energy doing so. And of course, the biggest issue of all of these strategies is you need to know what problem you work on. You need to know what your goals are. Are you going for high performance? Are you going for best energy consumption? And only then you know which approach to take. And it depends on your hardware properties, how efficient you can switch off cores, and so on and so on. So it really always depends on the use case. Now, almost finishing up here. I'm a little bit over time because we started late, but otherwise I hope it's okay. If any of you have to leave early, I won't notice, so don't worry. What I want to talk about a little bit are space filling curves, because they serve a really interesting purpose. Assume you have a two-dimensional problem domain, as we see here. What you normally would do is you would iterate through the entire thing by first going in one direction, say the x direction, and then going through the y direction. And this might be useful, this might be a good approach. However, you have the problem if you end up with a chunk of this size, for example. You might know this from cache optimizations, depending on what subjects or what courses you did in the past. As soon as you switch from one element to the next element in terms of a memory access, you will have the cache cold, and you will have to fetch this cache line, for example, into your cache. Because if you are contiguous in memory for the fastest changing index in x direction, that means these elements might fit into the same cache line, but elements that are above or below or something will obviously not be in the cache. And this is why sometimes it makes sense to not have a linearization, which is essentially what we're doing, in first going in one dimension, and once you reach the maximum of this dimension, you just add an additional element in a second dimension, and then again you go through the first dimension and so on. What you do with these kind of things is just you linearize your index, right? You try to arrive at the possibility of addressing a higher dimensional space with just one single number, which is exactly what happens in memory, because in memory, the virtual and the physical memory addresses of individual blocks of memory, of individual bytes, these addresses are just a single 1D index, right? There are no two-dimensional addresses in x86, for example. And the problem is that if we move up in the hierarchy and we go to domain decomposition and MPI communication, this might not be the smartest approach, because it might make sense to keep elements that are sort of close together in a physical domain also on the same rank or on the same node. And if we do pole decomposition, this might not make sense, because then we have a lot of neighbor exchange between ranks, because we have cells that are sort of close together. And remember, when we have cells close together in the physical domain, in the sense that they have an effect on each other, we want to keep them close together in our hardware mapping as well, in our domain decomposition. And something that can achieve this are space-filling curves. So in this case, I show you the example of a Hilbert curve, and there are tons of others. There's the Z curve, and I don't know which ones exist, which have all the same goal of linearizing your problem space. In this case, it's 2D, but it also works for 3D or higher dimensions, and making sure that elements that are close together in your original domain are accessed by indices that are also close together in your index space. So elements that are far off, for example, elements here in the bottom left and on the bottom right, are quite far apart in your physical domain, but with a normal linearization, they would be fairly close together. These two elements on the bottom left and bottom right would be closer together than elements here and elements here, for example, because you have to iterate through this row-wise, and this increases the distance in your linear index. With a space-filling curve, the distance is quite short. It's half of the distance of going through one entire row of your system, right? And there are many applications of these space-filling curves. A very interesting concept I came across once were navigation systems in cars, for example. Nowadays they use hard disks or SSDs with a fairly quick access time. But back in the day, when you didn't have that much storage in cars, they used to just read the data live from a CD-ROM or from a DVD that was in the drive in the car. And the problem is, if you switch from one CD track to another track, this really takes a lot of time, because you need to seek with your laser there. And they use space-filling curves to linearize their two-dimensional map in order to make sure that tiles on the map, for example, Tyrol and South Tyrol, which are close together, also close together on the CD-ROM, because if you then drive over the Brenner, you want to minimize the seek time it takes for the laser to switch to the next tile, and they use space-filling curves, because you will drive around with your car only from one cell to a neighboring cell. You will not immediately end up from going from Innsbruck to Copenhagen, for example. This won't happen. So it doesn't make sense to change to select an index scheme that makes sure that Copenhagen and Innsbruck are close together on your CD-ROM, right? So for this kind of things, you can use space-filling curves, which personally I believe is a quite interesting concept. And you have this all the time, these kind of patterns that end up in completely different use cases that were not originally planned, but it just works. Okay. Now finally, we're coming up, concluding the lecture, we're almost done here. Additional reasons for load balancing. You might not only have load imbalance caused by your program, but it could be external load caused by others. Not only on the CPUs, but consider, for example, the I/O subsystem or the network and so on. So you might want to deal with load imbalance that's caused by others and still make sure that your program sort of finishes fast. You just take into account the entire environment and all the surrounding conditions. You might have heterogeneous systems. I showed you the example of the Intel analyzer, the trace analyzer for Xeon PHYs and CPUs. So you might need to deal with static load imbalance because you have processing elements that do not have the same speed. And it could also be the dynamic availability of additional resources. For example, it could be that you're working on a cloud-based system, and at some point you get more cloud instances than you expected. It would be bad for them to go to waste, so why not just use them? And there are some cloud pricing systems or tariffs where you actually try to apply for cloud computing time. It's really cheap, but you do not have guarantees, or you have very few guarantees of how much time you get or when you get it. And if you can work with that, it's really cheap to work with those instances, but then you need to be able to cope with it in your application, obviously. And with that, we're done with load imbalance. I do have slides for Tales from the Proseminar, but those are just, again, the same slides that we already discussed previously. And I had a colleague, I can't remember who it was, showing that there's the efficient ghost cell exchange, which is not the one shown on this slide, because you have this implicit serialization where you have every rank waiting for its neighbor to complete the operation. And a much smarter way of doing is to do the neighbor exchange in sort of an odd-even pattern, where the number of communication steps that need to be done one after the other does not depend on the number of ranks. So on the previous slide, we need to wait for an n amount of time, and n depends on the number of ranks you have. And for this communication pattern, it does not. The amount of time required to do this operation is constant, doesn't matter how many ranks you have. So not the absolute time, but actually the time in the sense of how many communication steps you need to do. And I wanted to include those because I don't think I uploaded these slides yet, so in case anybody wants to take a closer look, they are part of this lecture set. And with that, I conclude the lecture. So we talked about domain decomposition, which is sort of a means of controlling communication overhead, both in the amount of data to be exchanged as well as in the amount of messages to be exchanged. The first one affecting the bandwidth that we need, and the second one affecting the latency that we need to endure. Afterwards, we talked about load imbalance or load balance, the difference between static and dynamic, how to recognize that we actually have this case going on. I showed you some examples, and for your own problems, just think about whether you have load imbalance or you don't, and how to be able to deal with those. Then just the tales from the Proseminar, which we didn't really discuss in detail, but just so they're part of this lecture slide set. And with that, I'm done with the lecture. Are there any more questions?